Okay, so to finish up talking about momentum, we're going to talk about Giancoli 7778. I'll talk about collisions in multiple dimensions. When we do this, this is very similar to breaking things down into vectors like we've done in the past, but we have to talk about this because not everything lies on a straight line. So, object moving in this collides with B, which is stationary. A shoots off in this direction, B shoots off in this direction, all right? But conservation of energy happens. So knowing the mass and initial velocity is not enough. We need to know angles to find final velocities. So that's where we have to think about things. Since things are vectors, we have to think about angles. So choose the system. Subsystems may be chosen, and that's when we talk about breaking things into X and Y components. Is there an external force? If so, is the collision time short enough that you can ignore it? That's something to think about. Draw diagrams of initial and final situations, and this is probably the most important thing. Show how things look, and then choose a coordinate system. I would always put something at the origin, but that's just me. Apply momentum conservation. One equation for each dimension for the X and the Y, and the Z if you're 3 dimensions, which we will not do. If the collision is elastic, apply conservation of kinetic energy as well. Solve it, and then check units and magnitudes of results. A lot of things to think about. And then another subject, center of mass. So we have 2 situations here. We have a person jumping straight up and coming down, and then a person doing all kinds of flips and doing a dive. In A, the diver's motion is pure translation. In B, it is translation plus rotation. So there's one point that moves in the same path, a particle. It would take some same force as the diver. This point is the center of mass. So you can see the center of mass of the diver here is just doing the straight up jump. Center of mass is the same spot. In the location here, as this diver spins around, though the point is the same, the center of mass moves based on where the diver's at in their rotation. But that's the center of mass. So the general motion of an object can be considered as the sum of the translational motion of the CM plus rotational, vibrational, and other forms of motion about the center of mass. So if we threw a wrench, and you know a wrench is way heavier on the end, on the end with the mouth as opposed to this end, but you can see the center of mass will stay even as the object rotates. The center of mass will stay constant. So for 2 particles, the center of mass lies closer to the one with the most mass, which should make sense. So here we go. So to find the center of mass, you have 2 objects, A and B, right? The mass of A times the distance plus the mass of B times the distance over the mass of A plus the mass of B. And then when we solve all of that, we can find the center of mass. So the place where you're the average between the 2 masses. Okay, so mass times distance plus mass times distance divided by the total masses. That's how you find the center of mass of an object. The center of gravity is a little different. It's the point where the gravitational force can be considered to act. It is the same as the center of mass as long as the gravitational force does not vary among different parts of the object. So here's our pivot point on this object. The center of mass is here. So is the center of gravity, and that's where we measure mg from when we do our work with it. The center of gravity can be found experimentally by suspending an object from different points. The center of mass needs to not be within the actual object, okay? So like a donut, right? The donut is in the center of the hole, so therefore it does not have to be solid. It can be something that's open. So here we have an object here, and we hang it here, and we can find the center of mass. And if we hang it here, the center of mass will be here. So we can find it suspending it from different points. I'm sorry, here, if we suspend it from this point, okay? So billiard ball collision in 2 dimensions. A billiard ball A moves at the speed of 3 meters per second in the positive X direction. It strikes ball B that's at rest. The 2 balls move off at 45-degree angles. Ball A above, ball B below. And what are the speeds of the 2 balls after the collision? All right, so here we go. We got A, mass of M, traveling 3 meters per second. We'll call this just VA. Hits a stationary ball B, all right? And then when they hit, then they break apart. So once they break apart and go at angles, we have to break things up into X and Y components. So I look at momentum in the x first. So in the x, right, I have this, which is the momentum here, which is mass times VA, so it's MVA plus M times 0, which is 0. In the y, which is here, there's nothing going on, so my initial momentum in the y is going to be 0. Okay, so now I look at x and y for both of these, right? So let's look at x first. X in the final momentum is going to be this component, which is going to be cosine. So with my mass m, it's going to be mass times velocity. So for A, it's going to be A's final velocity times cosine of 45 plus m times final velocity of B, and this is going to be negative cosine of 45. And then my y, we're dealing with the sine, so we're dealing with this component, the vertical component. So in the x, forming for A, it'd be m VA prime sine 45 plus m V prime B negative sine of 45. Make everything equal, so I'll combine my x's. So I'm making this equal to this, so I get m VA prime cosine of 45 plus m, I have to erase that, sorry, m V prime B negative cosine of 45. My m's cancel. So VA is going to be equal to all of this. When we look at here, right, that's going to be equal to 0, so I'm just taking what I had here and I'm making it equal to 0. I'll erase all this excess stuff and then I'll give you a chance to look at it. So you can see where we're at. I think you can, if we have a negative, so one trig function that comes into play here, and really what I would do if I'm solving this instead of trying to put everything in the equations is I would start to fill in numbers where I could. So here's what I know. I know VA is 3. So 3 is going to be equal to VA prime cosine of 45. I'm just going to get a decimal equivalent here. 0.707 plus V prime VV prime times the negative cosine of 45. Or the cosine of negative 45, I guess, is probably the better way to say it, which is also 0.707. Here, I don't have mass, but I can solve this then in terms of one or the other. So let's say I want to solve this in terms of VA prime. I bring this over, so I go 3 minus 0.707 VB prime is equal to VA prime 0.707. I just divide both sides by 0.707, and I have VA prime. I can take my VA prime, punch it into here, and I can solve for VB prime. So that's what I'll do. So now I got M times 3 minus 0.707 VB prime over 0.707. Sine of 45 is 0.707, right? Plus M V prime B negative sine, so the sine of negative 45 negative 707 equal to 0. So far, so good, right? So I can do some math here. These cancel out when I multiply them, and then I can bring this over. So essentially I'm going to get negative m times 3 minus 0.707 equal to m v prime b negative 0.707. My m's will cancel. I take 3 minus 0.707, and I get negative 2.293, and I get this, so I'm dividing then by negative 0.707. VB prime I can get then. Which will be 3.24. And then I just take my 3.24 and I substitute it back in here, and then I can solve for VA prime, which, believe it or not, will be the same answer of 3.24. That's what we're looking for here. And then we want to find the center of mass between 3 guys in a raft. So in a lightweight air-filled banana boat, 3 people of roughly mass m, so their mass is the same, sit along the x-axis at positions 1, 5, and 6 meters, measured from the left-hand end. Find the position of the center of mass. Ignore the mass of the boat. So we're just going to use the mass of other people. Do it now. Okay, center of mass. So we have our 3 people with relatively the same mass. And they're on a, I think they said it's a raft. Yeah, it's a raft. It's air-filled. And the distance is from the end. So this is N0. So this is 1, 5, and 6 meters from the end. And we want to find the center of mass of all of this. So remember, center of mass equation is we take mass times distance. So we go m times 1 plus m times 5 plus m times 6. So I just take the mass of each individual plus the distance from the center, and I will divide them by all the masses added together. So m plus m plus m. So I get m plus 5m plus 6m all over 3m. m plus 5 plus 6 is 12m divided by 3m. And so masses cancel. So I'm going to be stuck with the center of mass at 4 meters. So approximately right here would be my my center of mass. I think that's all we gotta do.